SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in this course Advanced Thermodynamics and Combustions. Today we are going to start the last module of this course, that is module 8, Combustion and Flames. In this module, on an average 5 lectures are planned. The first 2 lectures we will be discussing about laminar premixed flame. It will be followed by laminar diffusion flame. Then we will enter into the fundamental aspects of droplet evaporations and turbulent flame. And the last we will try to see the engine combustions and pollutions. And in fact, this particular lecture will be fully dedicated to the actual phenomena that happens in the engines, and due to the combustions in the engines and the combustions products that comes out to the exhaust, how it reacts with atmospheric air, and that leads to the pollution. So this is overall picture of this module. So let us start the first lecture, laminar premixed flame part 1. So in this lecture, that is lecture number 28, laminar premixed flame, we will cover the topics such as modes of combustions, physical features of a laminar flame, the factors that influences the laminar velocity, and flame speed correlations. So typically when you talk about flame, it is this flame speed that essentially decides how the reaction should proceed. If the flame extinguishes, means that it is not a self-sustained flame. So in order to achieve a self-sustained flame, we need to have a desired flame velocity. So in a laminar premixed flame, the flame velocity plays a critical role, and of course the temperatures, pressures, equivalence ratio, they all have adequate roles in that influences the flame velocities. So we will discuss them one by one. So let me start the first, to introduce the flame. Let us go back to very basics of combustions, which we started much earlier in our previous lectures. One point of time we discussed the modes of combustions, and to some extent we all know that combustion phenomena takes place in spark ignition engines and compression ignition engines. So in a spark ignition engines, the fuel and air, they mix before the charge enters into the engines. So it is a premixed combustions. And in a compression ignition engine, the fuel and air, they are separate entities, and they mix as and when they meet or admit at the some interface in the combustion chamber. So this is the very basic difference that makes the nature of the flame. So the combustion can occur in 2 types of modes. One is flame mode, other is non-flame mode. Typically in SI and CI engines, they are flame mode. So the flame mode is further categorized as premixed or non-premixed. Non-premixed flames are known as diffusion flame. So mainly in SI engines, the combustion is initiated through premixed flame, and typically mixed as well as non-mixed diffusion flames are part of CI engines. We will discuss about that. And if you broadly look at the flame and non-flame mode combustions, they are detected by knocking phenomena. For example, if you take an instant that in a premixed combustion in SI engines, there is a thin zone of intense chemical reactions that seem to be propagated in the unburnt air fuel mixtures. So, if you look at this particular figure, in a flame mode of combustion in SI engines, there is a propagating flame, and when the flame propagates, that means it is already reactants and oxidizers, they already have reacted, and it has created, as the flame propagates from left to right, the reactants and products, they mix together and they formed burnt gases, whereas in the other side of the flame we have unburnt fuel air mixtures, but still and slowly they gets reacted as and when the flame enters into their zone. Similarly, in a CI engines, when the flame moves, there is a regions where auto ignition takes place for the fuel and air mixtures. That is mainly because the fuel and air, they are considered as a separate entity, and they come and mix locally at one particular positions in the engine cylinders. So, that is the basic difference. Moving further, with respect to knocking. So, knocking is a very common phenomenon that leads to the sudden rise in the pressure in the engine cylinder due to the chemical reactions. And in fact, we all know that this knocking is undesirable in diesel engines, but we cannot avoid this knocking in compression ignition engines, because the auto ignition itself creates sudden rise in the pressure in the engine cylinders. So, with this viewpoint, if you take two classes of flames, one is premixed flame, where fuel and oxidizer, they are mixed at molecular level prior to the occurrence of chemical reactions. That is the very basic definitions when you talk about premixed flames. And the mixing takes place at molecular levels, and this mixture is nothing but a homogeneous mixture. But in contrast, if you look at diffusion flames, they are initially separated, and the reaction occurs only at the interface between the fuel and oxidizers, where actual mixing and reaction takes place. An example of diffusion flame is burning of a candle. Diesel engine combustion is mainly dominated by premixed as well as diffusion burning. So, we cannot exactly say it is a diffusion flame, it is a combination of both, but however, SI engine, it is purely dominated by premixed flame. But by definition, if you go back to combustion terminology, the way we defined the premixed flame, that mixing takes place at molecular level and mixture is homogeneous. In the similar context, we say that diffusion to the molecular level is achieved when the fuel molecules diffuse towards the flame in one direction, while oxidizer molecules diffuse to the flame in the opposite directions. So, basically we have fuel and air molecules, and they comes as a separate entity, and when the reaction takes place at the location of at the flame locations, we say that fuel molecules diffuse towards the flame in one direction and oxygen molecules diffuse to the flame in the opposite directions. This is the very basic definition for diffusion flame. And moving further, there is another concept of turbulent flames, and in turbulent non-premixed flame, the turbulent convection mixes the fuel and air together at microscopic basis, and in a molecular level or in the small molecular scales, the mixing process occurs in a very small domain or thickness, and that where the chemical reaction takes place. In fact, in most of the engine combustions, turbulence was created intentionally so that we need to have a proper mixing of fuel and air, and in particular that is in diesel engines. So, having said the very basic introductory part of the flame, we will now focus on to laminar flame. So, before you go for the laminar flame, let us understand how this laminar flame look like, or what is the basic definition of the flame. So, a flame is nothing but a self-sustaining propagation of localized combustion zone at subsonic speed. So, there are keywords like localized and subsonic. So, of course, why the word subsonic? Because at advanced version of combustions we can have supersonic mode of combustions where air and fuel movement is treated as a at supersonic speeds. But however, that is not part of the course, but to understand particular features of laminar flame, let us see that why this flame has to be localized, because it occupies small portion of combustible mixture at any time instant. If a flame exists, then it must contain the combustible mixture of fuel and air at any time instance. Now, there are two categories that we can have: deflagration or detonations. So, here deflagration occurs when discrete combustion waves they travel at subsonic speed, but when these waves travel at supersonic velocities, we call this as a detonations. So, our main focus will be the combustion phenomena at subsonic speeds, and we are trying to look into the characteristics features of this premixed flame. So, the dominant factors that is influenced for the existence of a laminar flame are its flame speed and flame thickness, and for this existence of this flame speed and flame thickness, we require appropriate environment. Means for a self sustaining flame, we require adequate equivalence ratio, temperatures and pressure, fuel types, all conditions needs to be satisfied. And in fact, the flame speed effectively detects the flame shape, stability, such as blow up and flashback. Blow up, flashback, something like either it can create an explosion, or it can the flame will be out of the domain, or flame will not exist. And all the other parameters, like we also require the flammability limits, ignitions, extinction. That means for a self sustaining flame, we need to put appropriate amount of energy, we call this as a ignition energy, and the flame to terminate, or flame to be terminated, we require flame extinction. So, all these things we are going to discuss for a laminar flame. So, before you do that, so let us understand the characteristics features of a flame, and that is decided through its temperature profile. We will come back to the temperature profile later, but let us understand that if you want to have a existence of flame, what should happen? The flame may be freely propagating when it is initiated in a tube in a combustible mixtures. The appropriate coordinate system must be considered. So, basically, if you consider a flame to exist, normally by definition we say in a one dimensional framework, if the flame has to exist, it has a very small thickness, and within this thickness we have reactants, products, and actual reaction that takes place. So, if you see that if there is some flame, it is traveling at certain speed. So, let us say if it is flame speed is SL and it is traveling at certain speed, then what we see is, if you say this is a flame, and when you are when you take the coordinate systems such that you are sitting on the flame and try to see in a one dimensional framework, you try to see where is reactants and where is products. So, so if you take this domain, you can see just before this flame, we will see that we will have burnt gases, which means flame has already propagated in these regions, and in the other side we have unburnt gases, which means it is a mixture of reactants or reactants, which that is fuel plus oxidizer, means that this flame has not entered to the unburnt regions, and when the flame crosses these burnt regions, already the burnt gases has very high velocities. So, that this we see when we are sitting on the flame. Now, with respect to laboratory viewpoint, you assume that you arrest this flame, that means flame is same flame, you arrest it and try to see where is the unburnt gases and where is the burnt gases. So, in a sense that if the flame is considered to be stationary right now, we can say that this unburnt products or unburnt gases, they enter at similar speed, at certain speed, and they come as burnt gases. And entire event that happens in this small thickness, which is nothing but the flame thickness. So, this viewpoint we call this as laboratory viewpoint analysis, and this is with respect to flame viewpoint. So, this is what we have explained here, that observer riding on this combustion flame experiences unburnt gases approaching at certain speed, and the flame is stationary relative to the laboratory frame for which reactants enter the flame with a flame's propagation velocity of SL. And in one dimensional and in a certain flame sheet of certain thickness 1 mm, let us say, we can see a one dimensional zone in which we can apply these continuity equations for a frontal area A that involves density as well as the speed. Now, the flame heats the products. Now, when we apply, we can write these continuity equations with respect to these equations, which says rho u SL into A, that is flame speed, is equal to rho u Vu into A, that is equal to rho B into Vb into A. So, A is your frontal area which will get cancelled, but what remains is that rho is the density, U stands for burnt gases, B stands subscripts U and B stands for burnt and unburnt gases, and we have flame speed SL, velocity V stands for velocity. So, this equation says that Vb has to be greater than Vu. Why? Because we can say that since the flame heats the products, the product density is less than reactants, and gas velocity is higher than the burnt gas velocity is higher than the velocity of the unburnt gases. So, because of these reasons, since Vb greater than Vu, so this equation needs to be satisfied. So, that means rho u must be greater than rho b, and much higher. Typically in a hydrocarbon air flame, this is about 7 times higher. So, this particular equation gives considerable acceleration of gas within the flame, and all these analysis are done with respect to one dimensional framework. Now let us understand another clear pictures. So, this is a generic figure that represents what happens in the flame. So, a flame is considered to have two distinct zones, one is preheat zone, other is reaction zone. So, the preheat zone is where the little heat is released, and reaction is the zone is where the bulk amount of chemical energy is released. So, if you look at this particular figure, we are looking at this axial distance versus heat release or temperature or mole fractions. So, as you go in these axial directions, obviously the concentration or mole fraction for the reactants drops, and when the reaction keeps on happening, temperature shoots up, and if you look at the temperature shoots very fast rate, and temperature also shoots up, and at the same time there is an enough heat release. So, we call this as a volumetric heat release, and this heat release is very instantaneous, and it takes a shape of a impulsive nature. So, it is like an impulsive heat load. What we see here is that if you divide this entire phenomena in two zones, one is preheat zone, other is reaction zone. So, during the preheat zone, not much of information we get about heat release or temperatures, but maximum reactions or changes that takes place in the reaction zone. And typically entire event that happens in a flame thickness which is nearly about 1 mm. And further, and if you very particular about reaction zone, it is further divided into further thin regions which involves fast reactions or fast chemistry as well as the slow chemistry. For examples, the destruction of fuel molecules and creation of intermediate species occur in the fast region chemistries, and in fact they are dominated in a bimolecular reactions. Now, again in the fast reaction zones where temperature and species concentrations are very large. So, in the reaction zone the temperature and species concentration are very large, and this and it has to be to keep this flame in a self sustaining mode, this temperature and species concentration should be high, and because they provide necessary driving force. Hence, we can say diffusion of heat and radical species from reaction zone to preheat zone can produce a self sustaining flame. And another kind of reactions also gets dominated when you take, and even that is in the secondary zone or reaction zone, in which the reaction is dominated by 3 body radical recombinations. What we discussed earlier, they are bimolecular reactions. Now, there are other possibilities that there are radical combinations of in the secondary reaction zone, where we can have the 3 body radical recombinations. So, when you say recombination, when the word recombination takes place, it normally slows down the reaction process. So, as a result, the formation of products gets the dominance. One such example, you can say that when CO and OH radicals they mix in the reaction zone, they form CO2. Once CO2 is formed, it automatically slows down, because again further dissociation is not initiated. The 3 body radical zones is normally considered as a recombination reactions. It slows down the bimolecular reactions. Another kind of study people have done is that for hydrocarbon flames, when you look at hydrocarbon flames and we try to see what happens in this reaction zone, we find that during during excess air reactions or in a lean mixtures, we see the flame to appear as a blue, and that is due to the presence of radical CH, and that happens in a high temperature zone. Now, when we come back or we reduce the excess air, that means we come back to stoichiometric, or we are entering into the fuel rich region, this zone becomes or the color becomes blue green. So, this is mainly due to the carbon atoms or C2, and in both the cases we get an effect called as chemiluminescence, which means CO reacts with oxygen to give CO2 plus H nu. H nu is the Planck's constant and nu is the radiation frequency of radiations. So, this frequency talks about which color gets dominated during the reaction process. Now, further when you enter into richer zone, that means when the flame gets more and more richer, it is obvious that we will have soot formations. Okay. And this soot formation that we have already analyzed, that when we are rich mixtures, soot formation is a very common effect. And all these things, again when we analyze the soot formations, we analyzed with the viewpoint of chemical reactions. Here we are going to look into the viewpoint of flame. Okay. Now, let us understand some mathematical background how a flame looks like. A standard example which can say is a Bunsen burner flame, which consists of a dual flame. So, if you look at a Bunsen burner flame, the entire idea is that we have slots, we have a tube, and in the tube in the bottom of the tube there are slots where air enters, and also there is a passage of fuel, and both mix and travel towards the upper regions. And what we see in the top is flame consists of two cones, one is inner cone, other is outer cone. So, inner cone is typically premixed, whereas outer cone is diffusion. So, what does this mean? That the fuel premixed inner flame is surrounded by a diffusion flame. The secondary diffusion flame is formed because in this carbon monoxide and hydrogen products from richer cone encounters the ambient air. So, the shape of the flame is further determined by the combined effect of velocity, profile and heat loss to the tube wall. Now, for the flame to remain stationary, the flame speed must be equal to the speed of normal component of unburned gases at each location, which can be illustrated in the following vector diagrams. So, let us see this particular figure. We have this inner cone, and in this inner cone geometrically we can say we can define an angle alpha, which is the local angle of the flame sheet that makes with a vertical flame. We have the unburned gas velocity, which is defined by VU vector, which comes from the bottom. Then we can define two components, one is the normal component, other is the tangential component with respect to this flame sheet, and based on this we can define laminar velocity SL is equal to VU times sin alpha. So, this is the basic definition of laminar burning velocity. Now, moving further, there are the consideration of the flames is normally adopted in various types of burners, and in the market available we have radiant burners, we have adiabatic burners, and what they produce? They produce laminar flames, and in the adiabatic burners we get stable flat flames, and in non-adiabatic burners we get stable flame, but very narrow regions, and in non-adiabatic flame we get same flame, but we get it in a over a wide range of flow conditions. So, typically depending on the requirement of the burners, we decide what should be the nature of the flame, and all of these things is decided whether we are retaining this flame speed or not, or flames or self sustaining flame or not. The next topic of discussion is factors that influences the flame velocity. So, the first two factors are obviously temperature and pressures. Laminar flame speed has a strong temperature dependence because the global reaction orders for the hydrocarbons is about 2. So, it is a kind of second order reactions, and for which the activation energy is quite high. It is about 1.7 into 10 to the power joule per kilomole. And the increase of temperature of burnt gases also increases the temperature of unburnt gases by the same amount when dissociation and temperature dependent specifics are neglected. So, this is the role of temperatures, and when you think about what is the temperature dependence, there are with respect to flame speed, the laminar speed is with respect to temperatures is given by this expression, which says that burning speed is proportional to the square root of temperature of unburnt gases. So, and these relations are empirical in nature, and it is very of course, and this holds good for most of the temperature ranges from 300 to maybe close to 1000 Kelvin. Another dependence of pressure, we can say that pressure laminar speed is proportional to or inversely related to pressures, and also the flame thickness is related to thermal diffusivity and the flame speed. So, basically if you look at a flame, it has certain thickness delta, it has a characteristic speed SL. So, SL is depends on temperature of unburnt gases and pressure, and delta is depends on flame speed and thermal diffusivity. So, and these simple relations are given through empirical correlations as shown in these equations. The next dependence factor that influences the flame velocity are equivalence ratio and fuel type. So, if you recall our earlier one of the figure which says that how the temperature changes during a reaction process with respect to equivalence ratio. If you talk about adiabatic flame temperatures, we have seen that for a methane air propane air mixture, the maximum adiabatic temperature is reached about 2278 Kelvin at slightly rich mixture, that is closely phi is equal to 1.05. So, in same philosophy we can say equivalence ratio as major role as that of temperatures. So, the flame speed is expected to be maximum at slight reach equivalence ratio, because the adiabatic flame is approaches peak value and it falls on either side. Okay. And this logic also is true for with respect to equivalence ratio. Another type of comparison with respect to fuel type, one can say we can make some distinction that hydrogen is considered to be one of the green fuel, and whereas hydrocarbon fuels are also considered as the which are being used in the conventional as a conventional fuel. And if you look at hydrogen, in a hydrogen combustion environment, hydrogen flame speed is higher than that of a propane or any hydrocarbon. That is mainly because thermal diffusivity and mass diffusivity of hydrogen is much more higher than the hydrocarbon fuels. That is one thing. Second is reaction kinetics for hydrogen is very rapid, because the relative slower reactions, that is conversion of CO to CO, CO to CO2 is absent. That carbon, that means one of the reaction process, there is a step where carbon monoxide changes to carbon dioxide, and this is nothing but a slow reactions, and these slow reactions of course affects the rate kinetics or kinetics and chemical kinetics, and which is absent in hydrogen, because hydrogen is a green fuel, and for which you can say the reaction kinetics of H2 is much higher. A workable model for flame speed correlations has been developed for laminar speeds. So, here we are going to discuss the laminar speed correlations with respect to pressure, temperatures and some dilutants. One thing I need to emphasize, while developing these correlations is with respect to particular fuel with certain reference conditions, and the expressions deal with some pressure and temperature exponents, and all these data sheets or data for the fuel types that can be available in the textbooks. What it says is that it has if you look at these particular expressions, the calculation of laminar flame speed depends on three factors, that is flame speed at reference conditions, the effect of temperatures of unburnt gases, effect of pressures, and then the effect of dilutants. That means, in many IC engines, what you do, we circulate the exhaust gas again into the engines. So, it affects the engine equivalence ratio. In turn, it has a negative effect with respect to flame speed. That means, flame speed reduces with the presence of dilutants. So, this means that the recirculation of exhaust or flue gases mix with incoming charge in most of the operating conditions, this reduces the flame speed. So, as you can see in this figure, and in fact, these particular relations holds good for temperature much above than 350 Kelvin, and if you use this formula for less than 350 Kelvin, we get a underestimate value with respect to flame speed. And for our study, we can say this laminar speed correlations is a very strong relations that can solve many numerical which can be used for solving many numerical problems for the combustion studies. Of course, this particular relations has dominant influence, we can say, with respect to temperature as well as pressures, and in particular while dealing with the turbulent flame analysis, the estimate of laminar flame speed plays a key role. So, this things is very vital in the study. So, okay, with this we completed this today's lecture parts. The second component we are going to discuss is the to solve some numerical problems based on our discussion. So, the first problem talks about a situations where we are considering a premixed laminar flame in a one dimensional gas flow, where the vertical velocity of unburnt gases varies linearly with horizontal distance as shown in this figure. So, we are supposed to find what is the flame speed, flame shape, distribution of local angle, and flame surface from the vertical for a stoichiometric methane air flame speed of 0.4 meter per second. So, basically the problem is nothing but we need to recall our study where we say that if you say we have a flame front which is plotted in a z-x coordinates, and if you take a flame sheet which is propagating, and we can draw one vertical which is nothing but your flame speed SL, and unburnt gases which can go as BU, and if you take the angle point of reference, then you can say this angle is nothing but your alpha, and this angle is nothing but beta. Okay. And what one particular point, and one particular point on this flame sheet we draw a tangent and configure this geometrical informations. And what the question is asked, we need to find what is this shape, flame shape. First thing, and distribution of local angle. Local angle means what is the how alpha varies with the distance. What is the data given? Data given is referred with respect to figure. Your vertical unbound velocity that varies in a distance 0 to 20 millimeter, and speed varies from 0.8 to 1.2 meter per seconds. So, and this variation is linear. So, this linear relation is given. So, we recall that laminar flame speed SL is equal to Bu sin alpha, so that we can write alpha is equal to sin inverse SL by Bu, right, and SL is given as 0.4 meter per second, we will write 400 millimeter per second. And what data from this figure we can get at x is equal to 0, we say Bu is equal to 800 meter mm per second, x is equal to 20 mm, Bu is equal to 1200 mm per second. So, this equation can give you the relation between Bu and x. So, you can write this linear equations as 800 plus the slope. Slope is nothing but 1200 minus this minus 800 divided by distance, that is 20 into x. So, you can write Bu is equal to 800 plus 20 x. So, the distribution of local angle, that alpha can be written as, so alpha you can write as sin inverse SL, SL is 400 divided by Bu, Bu is 800 plus 20 x. So, we get alpha as a function of x. That is the second part of the study. To find the flame speed, we need to find the z versus x. So, from this figure we can find what is dz by dx. So, dz by dx we can write as tan beta. So, by this trigonometric analysis we can say Bu, which is a function of x square minus SL square. So, this distance, this by this. So, this is your angle divided by SL square. Then we know Bu is 800 plus 20x and SL is 400 millimeter per second. So, you can write this equation as dz by dx as 800 plus 20x whole square minus SL square 400 square divided by 400 square. So, after simplifications this becomes 2 plus 0.05 x square minus 1. So, z of x is nothing but integration of dz by dx from 0 to x. So, we know dz by dx we can find the into dx. So, these equations can be integrated to get the flame shape. So, this is a very simple problem which we can be attempted, and this figure that takes about that how z varies with x, typically we are going to get it, and how alpha varies with x, that also you can see it is plotted here. So, ultimately what those plots we come here, that is represented through this equation. The second problem which we are going to discuss is about the comparison of laminar speeds of gasoline air mixture in a spark ignition engines at equivalence ratio 0.82 in three cases. One is temperature pressure conditions at reference situations, engine operating conditions, and engine operating conditions with an EGR. So, for that, the first equation that we are going to recall, that what is okay, the first case let us see. So, what is the data given? Datas are T reference. Normally this T reference is 298 Kelvin, which is already written in our previous slides. P reference is 1 atmosphere, that is your reference conditions, and fuel parameters at reference conditions are required as Bm is equal to 27.58 meter per second, B2 is minus 7080.34 meter per second, phi m is equal to 1.13. So, this data we obtained from the book, and that is Turn's book, and this data was taken for gasoline air mixture. Okay. So, this is the data given. Now, you have to recall what is the expression for SL. SL at reference condition is given by Bm plus B2 into phi minus phi m whole square. So, your data that is given phi as 0.82, and we all know that we have all these value Bm, B2 and phi m. So, inserting the value, we can directly get SL as 20 centimeter per seconds. Okay. B2 is given, Bm is given, phi is 0.82, phi m is 1.13. So, we get SL reference. The second part is we have to find with this SL reference data, we are going to get the engine at we are going to get the flame speed at engine operating conditions. So, we have to recall. So, there we have to give the dependence of pressure and temperatures. So, that expression SL at temperature Tu and pressure P, we can write SL reference Tu divided by T reference to the power gamma into P by P reference. So, what is data given? P is 18 atmosphere, Tu is 680 Kelvin. What we P to the power gamma into beta. So, exponent gamma is 2.18 minus 0.8 into phi minus 1. So, phi is 0.82. So, this gives gamma value as 2.234 and beta is equal to minus 0.16 plus 0.22. These correlations you have to use. 5 minus 1 minus 0.86 plus 0.222 into 5 minus 1, that gives beta value is minus 0.1996. So, by inserting this value, with this will give you beta, gamma, beta, P, P reference, T reference, all are known. So, this will give you or I can say SL at 680 Kelvin, 18 atmosphere, we will get this is 71 centimeter per second. So, you can see that SL at 680 Kelvin, 18 atmosphere is greater than SL reference. This is the first conclusion we say. Second part or last part, these same operating conditions, but with exhaust gas recirculations. So, in the same expression, when you say EGR is 18% or we can say it is 0.18, we write SL at TU, P and EGR is equal to SL, that is 680, 18 atmosphere, 680 Kelvin, 18 atmosphere, this value multiplied by 1 minus 2.1 Y dilutant. So, here the Y or mole or we can say mass fraction of dilutant is 0.18. So, Y dilutant is 0.18. So, this number when you calculate that SL, TU, P, EGR, that value is 44.2 meter per centimeter per second. So, this means your and that is less than SL at 680 K and 18 atmosphere. What it says, that exhaust gas recirculations decreases the flame speed, and higher circulation of EGR will have a great consequence in terms of flame speed, because it can arrest the flame to very almost 0 velocity. So, there are limited situations that exhaust gas can be initiated with certain level. So, with this I conclude the discussions for today. Thank you for your attention.